Hi, this is Mr. Maron. We're going to take a look at a quantitative projectile motion problem. This first problem just deals with horizontal projection, so no initial y velocity. We'll look at a little more complicated example afterwards. So here we have a ball rolling off the edge of a table with some initial horizontal velocity, follows projectile motion, and reaches the ground sometime later. So this question has two parts. The first part asks for how long does it take to reach the ground. The second part asks what's the speed of the ball right before impact. So for every projectile motion problem, you should make a little organizational chart, because for every single one, we're essentially interested in the same sets of quantities. And you can see for the y and for the x, and then the time, which kind of is the connection between the two. Now, why is y charts longer than the x chart? Well, y, you have to worry about an acceleration. In the x direction, there is no acceleration. And because there is an acceleration, that means that there's two velocities you could be interested in. Some initial velocity and some final velocity later on, whereas in the x direction there's only one velocity. So that should be the basic setup for every projectile motion problem. The next part is, does the problem give me anything obvious? Like, how can I fill in this chart to start out? Well, it gives me this, 1.3 meters, and the big mistake I see people make is not considering the negative. All of these are vector quantities, so all of them have direction. And we can talk about the y direction in one dimension and the x direction in one dimension. So we indicate those directions with positive or negative signs. So yes, it moves 1.3 meters, but it moves 1.3 meters down. Typically we define down to be negative. In the x direction, you want to recognize that this is a horizontal velocity. So that goes right here. It does not tell us anything about the y velocity. So that's where this is the step where you put in the obvious information from the problem. The next step is thinking about the less obvious information, things that aren't spelled out, but things that you have to know. In this problem, you need to recognize that the initial vertical velocity is 0. It doesn't spell that out, obviously, but you need to be able to interpret that from your knowledge of projectile motion, that there is no component of this initial velocity that tilts up or down. And you should assume that this takes place on Earth, so we can make the assumption that the acceleration due to gravity is negative 9.8 meters per second squared. This is not the same thing as g. It has the same numerical value as g, 9.8 meters per second squared, but that's a coincidence, right? The strength of gravity is not the same thing as an acceleration with the only force being gravitational. That's a small distinction, but understanding the difference between those two will make you understand why I have to include a negative here, this being a vector, and why when I'm actually plugging in g, when I see g in an equation, I don't put in a negative. So what are we interested in out of all these three unknowns? We're interested in time. So the next step is picking a kinematics equation that will help you out. At this point, I would pause the video and see if you can choose the correct kinematic equation. So I pick the first kinematic equation because the only unknown is time. I get an easy step right off the bat if I recognize that this is saying the initial y velocity. Way too often I see people trying to plug in this 1.6 meters per second, which was an initial x velocity, into this part of the equation right here. That is not the same thing, right? These kinematic equations only ever deal with these y components, whereas the x is only ever dealing with the constant velocity. So a big thing about understanding projectile motion is being able to understand the difference between x and y velocities. So the fact that this initial y velocity is 0 means that this term goes away, simplifies to that. We do a little bit of algebra to solve for t, plug in our numbers. Go ahead and check yourself to make sure you're not making any careless errors, but you get a time of 0.5151 seconds with a little bit of rounding. So that solves the first part of the problem. I'd also like to point out that this is the exact same solution as if we were to just drop the ball from that height, right? The x velocity, you'll see, never came into play for this solution. At no point did I plug in that 1.6 meters per second to solve for the time. It's because it doesn't matter, right? Whether you drop a ball or project it horizontally, it still has the same initial y velocity, 0. So it still hits the ground at the same time. Okay, so the next part says, what is the speed of the ball just before impact? Well, Go ahead and put in what you know from the previous problem that adds to our chart, that 0.5151 seconds, and realize that to find the speed, it's actually a two-step process. I first have to find the missing final component. So it's pretty simple to choose a kinematic equation. I chose the second one here. Could have chosen another one, but I chose the second one. Realized that the initial y velocity is 0. Multiply the time times negative 9.8 meters per second squared. I get the final y velocity is negative 5.0478 meters per second. Here's another mistake. People stop the problem here. They say the speed at the bottom was 5.04 blah 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 meters per second. That is not the speed at the bottom. That is the y component of the velocity. It's a different thing. Let's see how that is related to the speed at the bottom. So, if you think about the velocity vector of the ball right when it gets to the bottom, it's not going straight up or straight right. It's at this angle here. And it has components. It has x and y components, this final velocity. So this x component is exactly the same as this 1.6 meters per second. But this y component is what we just calculated. It's the same y component as if we were to just drop the ball from that height. That's that, from the previous problem, negative 5.0478 meters per second. So what it's asking for when it's saying speed is it's asking for the length of this overall velocity vector. Now that is a geometry problem, because if I know the length of this top side, the x component, I know the length of this right side, the final y component, then it is a matter of thinking about it as a right triangle to find the length of this hypotenuse, which is the magnitude of the velocity itself, or the speed. So doing that, I get 5.295 meters per second. The people who can't do this problem are the people who don't understand the difference between having an x velocity and a y velocity. Those are two things, two components of a vector that come together to make the actual vector itself. So we can talk about the length of either of those components, or we can talk about the length of the vector itself. So the length of the vector itself, the speed, is 5.295 meters per second. So I want to show you next a easier, maybe easier, I don't know, easier to me, way to solve this problem using a conservation of energy, something that we had not learned when we first had covered projectile motion. So what you can think about this is instead is a conservation of energy problem, where we start out with some gravitational potential energy because we're some height above 0, assuming that we call 0 this line of the ball at the bottom. We call that h equals 0. So we start with some initial gravitational potential energy. We also start out with some initial kinetic energy because we're moving at the top. And that's all going into kinetic energy at the bottom, so we can generate this equation. Next, we realize something pretty interesting. Notice this line here, the masses are canceling out. And that makes sense, because you should know from projectile motion that the mass doesn't matter. So calculating it a different way, the mass should still not matter, should not show up in our final equation. So that simplifies us to this line here. Another step of algebra, I can actually solve for the final velocity and plug numbers in here. Again, this is g. G is not the same thing as acceleration in the y direction. Numerically, it has the value 9.8 meters per second squared. But this is a scalar, right? A scalar is just a number. It has no direction. So I'm just plugging in the number here. I'm not plugging in that negative. The people who plug in that negative get confused because they're trying to take the square root of a negative at the end. You have to understand the difference. So that allows me to solve for the final speed, not the speed in one direction or the other, the final speed at all, because kinetic energy and energy in general does not care about direction. So, skipped to the wrong slide. So that allows for maybe a more straightforward method to solve for the speed and not have to deal with the Pythagorean theorem stuff, because this isn't talking about components, this is immediately talking about what you're looking for, the speed. So, and the very confirming thing about this is we get the same answer either way, which adds to the support of either model, makes either model more significant, hopefully. So hopefully that helped. Again, I would recommend trying to go through this problem on your own at some point later to make sure you can get all the parts. Okay, thank you.